Hello, my name is Irene Fernandez Villegas. I work as an associate professor at the Aerospace Structures and Materials Department in the Faculty of Aerospace Engineering in Delft. In this video, I will talk about the energy required to produce different semi-finished products, in other words, basic material building blocks used to manufacture aircraft structures. I will focus on metallic and on carbon composite semi-finished products, since, as you already know, they are typical materials in aircraft structures. In the case of metals, semi-finished products are plates, sheets, and billets. In the case of composite materials, a semi-finished product very popular in the aircraft industry is prepreg. Prepreg consists of fibers pre-impregnated with a very precise amount of polymer matrix, in other words, plastic. Composite structures are indeed composed of multiple layers of prepreg in multiple orientations, which are subjected to a temperature and pressure cycle to join them together and give the material its final properties. As you learned before, newer aircraft such as the Airbus A350 or the Boeing 787 favor the use of carbon composites in their structures. On the contrary, the structures of older aircraft such as the Boeing 737, the 747, or the Airbus A320 are mostly made from aluminum alloys. This shift in structural material from aluminum alloys to carbon composites is driven by a reduction in structural weight, which leads to lower fuel consumption and therefore lower emissions during operations. But how does this material shift influence the energy required to manufacture the aircraft? Manufacturing of carbon composite prepreg comprises three major steps: manufacturing of carbon fiber, manufacturing of polymer matrix, and pre-impregnation of the fibers with the matrix. Of these three steps, carbon fiber manufacturing is the one that consumes the highest amount of energy, approximately 70% of the total. Carbon fibers are manufactured through the pyrolysis of a precursor material. Roughly 90% of the carbon fibers currently produced use a synthetic organic polymer called polyacrylonitrile, in short PAN, as a precursor material. The other 10% are based on pitch petroleum or rayum precursors. Manufacturing of carbon fibers is a complex, very expensive, and as we saw before, a very energy-intensive process that comprises four steps. First, polymerization of the precursor material to create PAN of a certain molecular weight. Second, spinning of the PAN precursor into PAN fibers. Third, oxidation and carbonization, which is a series of heat treatment processes, usually within the 1000 to 3000 degrees Celsius range, that stabilize and burn off the non-carbon components in the original PAN fibers, resulting in tightly bonded carbon-rich fibers. Fourth, finishing processes which first entail the application of surface treatments and coatings, called sizing, to protect the fibers during subsequent processing and to enhance bonding to the polymer matrix. And second, winding of the fibers onto spools. The oxidation and carbonization step is the most energy-intensive, amounting to approximately 50% of the total energy consumed in the manufacturing of the carbon fibers. It is followed by the spinning process, which consumes approximately 25% of the total energy. When compared to manufacturing of aluminum sheets or plates, manufacturing of carbon composite prepreg is about 3.5 times more energy intensive. The major contributor to the energy consumed while manufacturing aluminum plates is the electrolysis process used to extract the aluminum from the stable compounds it forms in nature. So as it seems from this comparison, the material shift from aluminum alloys to carbon composites to build aircraft structures results in lower emissions during operations, but makes manufacturing significantly more energy intensive. The good news is that the carbon composite manufacturing industry is relatively young, and therefore it has ample room for optimization, with estimated potential energy savings that amount to 85%, considering both state-of-the-art best practices and ongoing research. Some of the most significant energy savings can be achieved in the oxidation and carbonization step during carbon fiber manufacturing. Short to medium term energy savings can be achieved by using on-site energy production, using more efficient furnaces, using enhanced heat transfer and heat retention systems, and implementing waste energy recovery procedures. In the longer term, the use of selective heating methods, such as microwave heating, which targets heating in the carbon fibers, is expected to further increase energy savings. Another important future energy saving approach is the use of alternative, less energy-intensive precursor materials such as polyolefins, or, very important for a circular economy, recycled carbon fibers. In summary, selecting the lighter weight material is not necessarily the most sustainable solution for all phases in the life of the aircraft. Indeed, manufacturing of carbon fiber composites is several times more energy-intensive than manufacturing of aluminum plates. Fortunately, there is still ample room for improvement in the carbon fiber manufacturing industry.